All right, before we head into some of the other reactions we need to talk about, we're going to step back to cycloalkanes for a moment. Specifically, we're going to step back to the wonderful world of cyclopropane and three-membered rings. Now, we're going to do that for a reason. One, we're going to be making cyclopropanes later on in this chapter, along with other three-membered rings, but two, we're going to be using them, and we need to kind of review a few things about them first so that we're clear on them. First, importantly, the angle thing. Remember that we had to distort things pretty badly to get this to sit in this particular orientation. The orbitals are not on the axis of the bonds. We'll get to that in a moment. But importantly, what I'm seeing most commonly when I look this up is that this angle, I knew it was expanded, but the value I keep coming across is about 115 degrees. So what that means is that these two groups, whatever they are, hydrogens in this case, are moving dramatically apart from each other, from the ideal 109. Now, it doesn't sound all that dramatic, but what it means is that for anything larger than a hydrogen there, that carbon is going to be a little bit less blocked, which means our restrictions on things like SN2 reactions are not going to be quite as tight. That's important as we move forward because there's going to be some odd things there that are a little hard to explain any other way. Okay, second, those orbital overlaps. Now, if we looked at it just with the atoms, well, we drew these out like this before, that we had this kind of non-linear overlapping where this would be the axis of the bond, and I only need one of them, so I'm going to draw the other two in as regular bonds. That off-axis bonding means that we have a weaker overlap of the bonds and therefore not as strong of a connection between those two atoms. That's going to be very important to us as we move into the next chapter, as we move into some of the other reactions in this chapter, because we're going to use three-membered rings for a lot of stuff. So, here we go. First, just so we're familiar with them, the ones that are neutral that come up quite often. One, of course, the cyclopropane. We've been there before. We know this one well. Lacks any polar bonds, so is a little bit more stable and more reasonable to deal with. We're going to talk about that again when we make it later on in the chapter. Two others that are neutral that come up fairly often. The first you've already seen, it was on your second exam, is Oxirane. So this is sometimes called an epoxide. As a functional group, we call it an epoxide. The ring itself, naked like this, is Oxirane. This one has a lot of uses, and we're going to talk about making it in this chapter. But you saw this on your previous exam. The idea is that we have, or on the sample exam I gave you, is that that strain gives us a leaving group we would not normally have. Normally, a neutral oxygen, single bonded only, is a very poor leaving group. But because of the poor overlapped bonds that we saw in the previous page, that makes Oxirane particularly reactive. It undergoes SN2 reactions where normal ethers never would. The other, which we won't talk much about now, but will come up a lot later if we talk about medicinal chemistry, is aziridine. I can't get to the edge of the page here. So this is aziridine. Some of the same issues. More commonly, we're going to deal with that one later. It gets protonated since nitrogen is considerably more basic than oxygen. So then, of course, we clearly have a leaving group and a driving force to open that ring. But again, we don't need that one right now. That one we don't discuss in this chapter really at all. But I include it for completeness here. So we've got cyclopropane, oxirane, and aziridine. These are the neutral three-membered rings we're going to deal with frequently, all of which have the issue with those weird overlapping bonds. And there are two others that we need to talk about in the context of this chapter. We have to be a little careful about how we use them. First, these are both intermediates. They are not neutral, stable compounds on their own. First is a mercury version of it, which is cationic and generally has some other group on it. So this is an intermediate we're going to talk about that forms during the course of a multi-step process. Big caveat here, mercury is frigging massive compared to carbon, oxygen, or nitrogen in the cases above. So this is a much less stable structure to begin with. We're also going to have to include things like the d orbitals to explain it entirely. So it gets to be a little bit messy, but it is a valid intermediate and one we have to think about and one we're going to see again very, very quickly in the next video. The last one, which we'll see later on in the chapter, is a similar problem with a halogen. Most commonly bromine, but it does happen with chlorine as well, called a bromonium ion. So this is, again, an intermediate in a reaction, a step along the path to getting a more complicated reaction done, but it introduces those problems that we saw in the previous slide. That is, it introduces that weird overlap of the bonds. It also introduces a change in the bond angle for things that might still be attached to that carbon, say here and here. Well, those are now going to be further apart angle-wise than they normally would be. So that angle is going to be increased from a normal sp3 because of the decrease here in the ring. And that's true for all of these, but it's a bigger deal here in these two intermediate ones because the ring has to be so distorted because of the size of these monsters. So we're going to come back to this in some detail in individual examples, but I want to kind of get the basics of the three-membered rings back in your brain, and also the terminology. So again, Oxirane, this is a mercurium intermediate, mercurium cation, and this is a bromonium ion, cyclic bromonium ion. So when I use those terms, you'll know what they mean. All right.